So we're on to sequences now. Sort of patterns specifically with numbers is what we'll be looking at. Where there's a list of numbers and you're determining what do they have in common? What's the clue that leads you from one number to the next? And can you continue that sequence? We all learned number sequences when we were young in elementary school. You might not even think of them as sequences. The natural numbers, the counting numbers, 1, 2, 3, 4, 5, that's a number sequence. It's taking one number, starting with 1, and then just adding 1. 1 plus 1 is 2, plus 1 is 3, plus 1 is 4. That's a numerical pattern. The natural numbers show sort of our very first number sequence that we learn. Even numbers, 0, 2, 4, 6, 8. You start with 0 and then just keep adding 2. There's another number sequence. Can you think of others? Odd numbers, obviously, starting with 1. Again, add 2. 1, 3, 5, 7. And so you have to learn how to teach those concepts. And so recognizing patterns requires observation, like we did in the last video, and often making an educated guess, right? Sometimes it's making an educated guess. A lot of the times when you're teaching those ideas, you will use manipulatives, M&Ms, right? Pennies, something, right? That kids can touch and move to illustrate these quantities, helping them associate. This is maybe one of the most important things, associating numerical symbols with actual amounts. One of the things I used to do, this is a teaching tip that I would say from my own experience. I learned that one of the most important foundational ideas developing number sense is to do something called subitizing, which means, and we all do this as humans, seeing a quantity of things and immediately recognizing that that represents 4 without physically counting them, okay, with your fingers. And so to start, you kind of have to do that. But what you eventually want to be able to do is just see the grouping and say, I know that's 4. I know that's 2. I know that's 5, just from seeing it. And so I used to ask my son, right? I would hold up fingers. I would say, how many is this? And make him sort of look at the grouping to notice it's 2. And so those are important elements of learning number sense from a young age. So we're going to talk about some different number sequences here. And the first one is maybe my favorite. It's absolutely one of my favorite. And maybe it's something that you have heard of. It is called the Fibonacci sequence. Fibonacci sequence. So the Fibonacci sequence, I'm just going to dive right in. It starts like this. I'm going to write down the first few numbers in the Fibonacci sequence. 1, 1, 2, 3, 5. I'm going to start with that. Pause the video. If you've never seen this, if you don't know what it is, pause the video and see if you can figure out what the pattern is. If you can't, I'll add a few more numbers. So go ahead and pause. So if you're not sure, predict the next number. I'm going to keep going. I'm going to put a few more numbers out there, which may help. The next number is 8. The next number is 13. The next number is 21. The next number is 34, and so on and so on. So I'll let you pause again if you didn't have it figured out the first time and see if that helps. So the Fibonacci sequence is this. It is to get each number, each successive number in the sequence, you get it by adding the previous 2 numbers, right? So we start with 1, and then there was really nothing in front of the 1. We can even think about there kind of being a 0 there, even though it's not part of the sequence. So we just start with 1, and then we have 1 again. But then where does this 2 come from? 2 comes from 1 plus 1, the previous two numbers. The next number is 3. Where does the 3 come from? 1 plus 2. Where does the 5 come from? 2 plus 3. Where does the next number come from? 8. 3 plus 5. And so on, and so on, and so on. 13 is equal to 5 plus 8. 21 is 8 plus 13, etc. And this sequence continues indefinitely. And then it may be something you're thinking, well, so what, right? What's the deal with this? Why is that an important sequence? It is one of the most important mathematical sequences. It connects to nature everywhere. These numbers start to show up in lots of things in nature. Some of the famous ones would be the spirals in the center of a daisy, right? The number of petals, right, in a daisy, or this arrangement of spirals in a pine cone. You start to count these things, and there are these Fibonacci numbers. So many things in nature have this many number of things. When you start to count elements that are consistent or that are common, they will have a number that's in the Fibonacci sequence. It shows up in probability when you start to calculate probabilities, algebra, even when you start to multiply polynomials together, musical scales. The Fibonacci sequence is really everywhere within our world. It leads to something called the golden ratio, which has often been said as like the most beautiful, is aesthetically pleasing dimensions of a rectangle. And it shows up in architecture, historical, like Greek architecture has these things everywhere. There is even zoom out of the share. Another connection to teaching and learning. There are books are very important. Reading is obviously very important, especially at a young age. And there are so many good mathematical books for young kids also. This is one of my favorites. This is called Blockhead, The Life of Fibonacci. And this was, I used to read this to my son all the time. It's a kid's book, but it also talks about the story of Fibonacci and his number sequence. There's actually a famous story the question was posed with rabbits and reproducing rabbits. And so maybe you even Google that to see where his original idea came up with. So there's an interesting one. Another one of my favorite books that I used to read my son all the time. There are 3 of these. These are the best. It's called Penrose, The Adventures of Penrose the Mathematical Cat. And so these are full of like 2 or 3 page stories, and they're all about just sort of mathematical discoveries, but they're written in a way in which kids can understand them. Again, it introduces, this is one right here where it talks about even the Fibonacci sequence. You'll see the picture of that Nautilus shell. That is part of the Fibonacci sequence. This one's actually called Penrose meets Fibonacci Rabbit, right? And so there's 2 or 3 page mathematical stories that kids can really understand. And so it's okay to get math books, right, for kids as well. So another famous number sequence is it's partly a sequence, but it's also there's a visual that goes along with it, and it is called Pascal's triangle. Let's change it back to black here. Pascal's triangle. Oops. Triangle. Blaise Pascal, right? These were famous mathematicians. And so I'm going to just start writing some numbers down, and your job is to make observations and see if you can predict things. So at the top of this triangle, I'm going to write the number 1, and we're going to call this row 0. A lot of times in math, we start with the 0 number. So we're going to call this row 0. And below it, we are going to have 1 and 1. So those are in row 1. Below it, we're going to have 1, 2, and 1. 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 1, That's in row 2. Below that, we will have 1, 3, 3, and 1. That's row 3. And in row 4, we will have 1, 4, 6, 4, and 1. So pause the video and see if you can observe the pattern and write down the next 3 rows. I will go ahead and pause the video, and then I'll continue momentarily. So I'm gonna hope that you were able to figure out what numbers would be in rows 5, 6, and 7. So what observations did you make? In each row, we had new numbers. Well, where did those numbers come from? Those numbers came from the 2 numbers right to their upper left and upper right. So where did this 2 come from? 1 plus 1. Where did this 3 come from? 1 plus 2. This 3 came also from 1 plus 2. The ones continue because it's kind of like 1 plus, like an invisible 0 there. Where did this 4 come from? 1 plus 3. 6 was 3 plus 3. 4, 3 plus 1. So if we continue that, we should be able to figure out each successive row. Here we're going to have 1. 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5. And then that 1 carries down. Notice how it's also symmetrical on each side. Row 6 will be 1, 6, 15, 20, 15, 6, and 1. And I'm going to, just for the sake of neatness, just copy and paste this so you can see what it looks like in its full glory, the Pascal's triangle, right? So here is what Pascal's triangle looks like. And again, we will even see this show up a little bit later in some things that we do. It's really a cornerstone in understanding many higher level mathematical algorithms. And so even before we go on, I'll ask you to pause the video and just see if there are any other patterns that you happen to notice within Pascal's triangles. Just look around and see if you can notice some things that maybe we've talked about and maybe we haven't, other sequences, other patterns. So let's move on and talk about another type of mathematical sequence. So at the beginning, I mentioned in our overview of terminology, something called an arithmetic sequence. I'm going to do these two at the same time, 2 different types of sequence. That is an arithmetic. I know that looks like the word arithmetic, but it's pronounced arithmetic sequence. So an arithmetic sequence. And then we're going to also talk about, compare it to what's called a geometric sequence. So I like to make you do the observations. So what I'm going to do is I'm going to write down an arithmetic sequence. And then let's start with an arithmetic. So I'm going to go 2, 4, 6, 8, 10. Okay, that's an example of an arithmetic sequence. An example of a geometric sequence could be 2, 4, 8, 16, 32. So the first thing I want you to do is observe, right? Pause and see if you can notice any differences between those two and make a prediction on what you think might be maybe the definition of an arithmetic sequence or geometric sequence, and can you find the next 3 numbers in those? What I'm going to do is actually do another arithmetic and another geometric. So here's another arithmetic sequence. We'll go 7, 11, 15, 19, There's another arithmetic sequence and another geometric sequence. Let's do 3, and let's go 9, and let's go 27, and let's go 81. Okay. So again, pause, make some observations. Did your initial prediction align with here or not? Or do you need to make a change to what your initial thought was? So what is the difference between an arithmetic sequence and a geometric sequence? When you're doing an arithmetic sequence, to find the next number in it, you're going to add or subtract something. I say subtract because you can also add negative numbers. It basically means it increases each successive number increases by a constant value, and we call that the common difference. A common difference. Each number here is plus 2, plus 2, plus 2, plus 2. So what would the next couple numbers be? 12, 14, 16. It's really just the even numbers. For this one down here, what's the common difference? It's plus 4, plus 4, plus 4. So what would the next number be? If you said 23, you got it. So what's the geometric sequence then, if it's not increasing by a common difference? Geometric sequences increase by what we call a common ratio. Common ratio, which means you are multiplying by something to get the next term in the sequence. If you want to find out what that is, you're going to divide any number by its previous term. 32 divided by 16 is 2. 16 divided by 8 is 2. 8 divided by 4 is 2. So to get the next number in the sequence, we're going to multiply by 2. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. 16 times 2 is 32. 32 times 2 is 64. And then 128. And then 256. On this one, what were we doing? We were multiplying by 3. 3 times 3, 9 times 3, 27 times 3. What's the next number? 81 times 3 is 243. So those are arithmetic and geometric sequences. And so just as a little quiz here, a little quick check for understanding, I'm going to give you 3 sequences, and your job is to identify each sequence as arithmetic, geometric, or neither. Neither. So that's your question. So here we go. The first one is 2, 6, 18, 54, 162. The next one is 1, 4, 9, 16, 25. And the last one is 43, 55, 67, 79, 91. So pause, take a second, and see if you can identify each of those properly. So when we are looking at these, we're looking to see, is there a common difference? Is there a common ratio? Or if not, then it's neither. So in this first one, 2, 6, 18, 54, 162, what were we doing? We were multiplying by 3 each time. So what does that mean? It means this one is a geometric sequence. What about this one? 1, 4, 9, 16, 25. Did you find out what the pattern was? Well, were we adding something? Was there a common difference? Well, this is plus 3. This is plus 5. This is plus 7. That's not the same. Were we multiplying by something? 1 times 4, well, that's times 4. 4 times, oh, that doesn't get us 9, does it? Ugh. So this is actually a pattern, a sequence of squared numbers. 1 squared is 1. 2 squared is 4 when we multiply a number by itself. 3 squared is 9. 4 squared is 16. So it is a numerical sequence. It is a pattern, but it's not necessarily an arithmetic or geometric sequence. So we're going to say that's neither. What about here? 43, 55. Well, we're adding 12. Is that consistent? 55 plus 12, 67 plus 12. It looks like we found a common difference, which means it is arithmetic. That is an arithmetic sequence. Good. So let's move on. Let's talk about another type of sequence. This is the fun one. So this one is called triangular numbers. Triangular numbers. To introduce this section, remember I talked about natural numbers and odd numbers and even numbers. Well, triangular numbers are another type of mathematical, numerical sequence. And they have to do with an associated number of dots. Okay, so we're going to draw some pictures and then count things. So the very first one we have, I'm just going to make I'm going to make our sequence using dots first, right? So our first is just 1 dot. Our second is 3 dots. Our third is 6 dots. Do you notice a pattern? Fourth is, maybe you can guess, maybe you can start to see the pattern and make a prediction. Did it have 10 dots? Your prediction? Yeah, so the very first triangular number is the number 1. The second triangular number is the number 3. The third triangular number is the number 6. The fourth triangular number is the number 10. Can you predict how many would be in the next one? Go ahead and pause and find the next 1 or 2 triangular numbers. So here's a cleaner look at what those look like. The T stands for triangular number. One of the things you'll often see, a notation, a mathematical notation, is this, where we put a subscript, right? This little number down there. It's like a notation, right? So triangular number 1. It doesn't mean any sort of thing you have to do with the numbers. It's just a way to identify what we're talking about. So T1 means the first triangular number. T sub 2 is the second triangular number, so on and so on. So the fifth triangular number would be 15. You can see the dots. The sixth would be 21. And we could keep going and going and going. So I have let's see, a couple questions for you. And one is, I'm scrolling through some of my notes here. Could we find a formula? Could you find a formula, some sort of mathematical formula to predict how many dots were, say, in triangular number 20? Could we predict that? Could we find a way? Okay. So that's one of the things I want to leave you with for just a moment, right? Pause the video and see if you can make a prediction without doing just drawing them out. Can you find out how many would be in number 20 and come up with a mathematical formula? So did you come up with your formula yet? Did you notice anything? Does that look familiar? Did that process sort of ring a bell at all? If you were going to try to find the 20th triangular number, what you'd really be doing is adding the number 1 plus the number 2 plus the number 3 plus the number 4 plus the number 5 plus the number 6, right? That's how many dots are in each of these rows, plus 7 plus 8, all the way down to 20. So you'd be doing 1 plus 2 plus 3 plus all the numbers to 19 plus 20. Didn't we do that in the previous video? Isn't that something that we did in the previous video? Do you remember the formula? Remember how we were linking 20 and 21, 2 and 19? We did something like this previous. It was that Gauss had that formula that he came up with. And it was, if you want to find any number, triangular number, it's the number that you're looking for times one more than that number, n times n plus 1, divided by 2. So if you want to find the 20th triangular number, the formula is 20 times 21 divided by 2. And in this case, that would come up to be 210. 210. I can prove it, right? We can look at an example just to observe. Let's look at that T sub 6, right? So triangular number, sixth number. If you take 6 times 7, there's your n, the triangular number you're looking for. And then this is 6 plus 1, so 1 more than 6, divided by 2. 42 divided by 2 is equal to 21. And that's always going to work. Okay, so that formula can be used for any triangular number if you want to find that. So this is called a triangular number is based on the number of a geometric figure, right? So numbers that are based on some geometric figure have a name. And they are called figurate numbers. Figurate numbers, right? And there are other types of numbers as well, besides just these triangular numbers. And so before we go on to the next sequence, what I also want you to do, I want you to take a look at these triangular numbers that we had. Let me highlight them. So we have the numbers, the triangular numbers 1, 3, 6, 10, 15, and 21. Take a moment and look back at Pascal's triangle and see if you notice anything. See if you notice anything. What do you see? I asked you to make observations about that, right? If you look down the diagonals, you'll start to notice something. This first diagonal is just the numbers 1 over and over. The second diagonal is just our counting numbers, our natural numbers, 1, 2, 3, 4, 5, 6, 7. What did you notice about the next diagonal? 1, 3, 6, 10, 15, 21. Triangular numbers. That diagonal actually is triangular numbers. A lot of these mathematical ideas and patterns and sequences all start to be connected, which is so cool, right? That always just fascinates me whenever I start to notice those things and talk about those things. I love it. So let's move on. We've got one more sequence to talk about in this video, and it is called, they are called finite differences. Finite differences, right? We've talked about arithmetic, geometric, triangular, Pascal's triangle, Fibonacci. So let's look at another type, this finite difference. So I'm just going to give you some numbers: 0, 3, 8, 15, and let's go one more. Let's go 24. Okay. And so pause the video and see if you can find, let's just find the next number in the sequence, right? Can you find the next number in the sequence? So when you first look at this, you're going to stop, you're going to observe it, notice things. Is it any of the things we've talked about so far? Is it arithmetic? Is it geometric? Well, if we look at the differences, is there a common difference? Well, this is +3, 0 plus 3. This is +5, 8 plus 7, and this is +9, right? So there's not a common difference. There's not a common ratio either. We can't multiply by some common number. But one thing you might notice is that once you get the first layer, that first row of differences, there's actually a pattern in the differences. 3, 5, 7, 9. To go from 3 to 5 is +2. To go from 5 to 7 is +2. To go from 7 to 9 is +2. So this this second difference is constant, right? So sometimes it's not the first level of differences. The first level of differences almost establishes a new sequence. It's this second level, right? The second level of differences. If that is common, that's what we call, this approach is called having finite differences. So what would the next number in this sequence be? We kind of have to work through two problems, right? If we know that 24, we're going to add something to 24, we just have to figure out what it is. Well, 3, 5, 7, 9, if we add 2 more to 9, we get 11. That's going to be what we add to 24 to get 35. If we did one more, we'd have to add 2 to the 11 and add 13 to 35, which would give us 48. And so this is the idea of finite differences. And so one of the cool things, right, is that all these patterns, like I said, show up in so many different areas of mathematics and nature and just our sort of life around us. And so there's sort of an introduction to some of the types of patterns and sequences.